Hello learners. Let me ask you something. Have you ever tried to solve a quadratic equation and wondered how we can tell what kind of solutions it will have without actually solving it? Well, let's uncover that mystery together. We begin with the general form of a quadratic equation, ax squared plus bx plus c equals 0, where a, b, and c are real numbers and a is not equal to 0. To find the roots of this equation, we use the quadratic formula x equals minus b plus or minus square root of b squared minus 4ac whole divided by 2a. These values of x that satisfy the equation are known as the roots or solutions. But here's the secret ingredient: the expression under the square root, that is b squared minus 4ac, is called the discriminant. And it holds the key to the nature of the roots. Let's dive deeper into this special term, the discriminant. It is denoted by capital D and defined as d equals b squared minus 4ac. This value helps us understand what kind of solutions the quadratic equation will have even before solving it completely. So why is it called the discriminant? Because it literally discriminates or tells apart the types of roots, whether they are real or imaginary, equal or distinct. Now, depending on whether this discriminant is positive, 0, or negative, we get different kinds of roots. Let's explore each case one by one. First, what happens if the discriminant is greater than 0? That means d is greater than 0. Now the square root of a positive number is real, so the two values of x will be x equals minus b plus square root of d divided by 2a and x equals minus b minus square root of d divided by 2a. These two values are real and different, so we get two distinct real roots. Let's take an example. X squared minus 5x plus 6 equals 0. Here, a equals 1, b equals minus 5, c equals 6. So, d equals 25 minus 24 equals 1, which is greater than 0. Hence, the roots are x equals 3 and x equals 2. See how the discriminant helped us know the roots would be real and unequal? Now, let's see what happens when the discriminant is 0. That means d equals 0. In that case, the formula becomes x equals minus b plus or minus square root of 0 divided by 2a. Since the square root of 0 is just 0, both roots become x equals minus b by 2a. This means we get two equal real roots. Try this example: x squared minus 4x plus 4 equals 0. Here a equals 1, b equals minus 4, c equals 4. So, d equals 16 minus 16 equals 0. Thus, both roots are equal and real, and they are both 2. Alright, now comes the interesting part. What if the discriminant is less than 0? That is, d is less than 0. The square root of a negative number is not real, it's imaginary. So, when d is negative, the quadratic equation has no real roots. Let's look at this example: x squared plus x plus 1 equals 0. Here, a equals 1, b equals 1, and c equals 1. So, d equals 1 minus 4 equals minus 3. Since the square root of minus 3 is not a real number, we conclude that this equation has no real roots, only imaginary ones. To wrap it all up, let's organize everything in a neat summary. We say that a quadratic equation ax squared plus bx plus c equals 0 has different kinds of roots based on the value of the discriminant d. If d is greater than 0, we get two distinct real roots. If d is equal to 0, we get two equal real roots. If d is less than 0, there are no real roots, only imaginary ones. So the discriminant is like a magic number that predicts how the equation will behave. You can also visualize this with the graph of a parabola. If it cuts the x-axis at 2 points, d is positive. If it just touches the x-axis, d is 0. If it never touches the x-axis, d is negative. Isn't that a powerful insight? Let's quickly revise what we've learned today. The discriminant d equals b squared minus 4ac tells us the nature of the roots of a quadratic equation. We saw how d greater than 0 gives to distinct real roots, d equals 0 gives to equal real roots, d less than 0 gives no real roots. This concept is not just theoretical, it helps us quickly analyze and predict solutions in real-world problems like motion, area optimization, and economic profit models. I hope now you understand how the discriminant works and how it simplifies our understanding of quadratic equations. See you there.